Information theory, but before we come to that, I'd like to motivate why we need to study information theory to understand better the basic principles of digital communication. To do that, let me first summarize what we have learned so far in a nutshell in terms of digital communication over a noisy channel. Right? Suppose we were to summarize our knowledge in a nutshell, then what we have learned is something like this. First, we have learned that communication can never be error free, right? As when you're talking about digital communication, transmission of symbols or bits, invariably due to noise and other distortions, and at the moment we are only concerning ourselves with noise, there are going to be errors. So that is the first lesson from our discussion so far. Okay, there is always a certain error probability associated with whatever modulation, demodulation scheme or whatever coding scheme you might employ, right? We can reduce this error probability. That's the second thing we have learned. The error probability can be reduced but cannot be made zero, right? It can be made zero only asymptotically. P can be reduced, but if you want to really reduce it to zero, that is make the communication really error free, then you'll have to take recourse to one of the two things, that is increase your signal to noise ratio, and you'll require this increase to go to infinity if you want your error probability to go to zero, right? Because if you look at any expression for the error probability that we have derived, whether it is for binary or memory system, whether it is for coherent or non-coherent systems, you will see that asymptotically each of these expressions becomes zero as EB by N0 is made to go to infinity, right? Because asymptotically all of them are of this kind. Asymptotically, if you look at any of these expressions, whether it is in terms of Q functions or any other kind of function, asymptotically you will see that you can approximate it as e to the power some constant times EB by N0, right? Now this implies that you have to either increase the signal power. This to increase EB by N0, again there are two ways, right? You can increase your signal power transmitted signal power, or alternatively by increasing your interval of one bit or one symbol, increasing your bit duration, or in other words decreasing your data rate, transmission of rate of data, or decreasing rate of transmission. Is it obvious from this expression? Because EB is what? It is the energy per symbol or energy per bit actually, right? So you want to increase this to infinity. There are two ways. Either you increase the signal power to infinity, because energy per bit is going to be proportional to power times the duration of each bit, right? So either you increase the average power, pump in more and more of power as you can do, or alternatively you reduce your data rate. In fact, if you want it to be infinity with a finite amount of signal power, the data rate has to be reduced to a trivial value of 0, right? So therefore it seems that there is no hope of reducing error rate to a level of 0 errors eventually in a practical sense of the word, right. That is, either you go for infinite power or go for trivially low data rates. Now this was a classical view of communication theorists till let's say a particular gentleman came into the picture, and that was before, I think, in the year 1948, when Claude E. Shannon came into the picture, and he changed the view of communication theorists regarding this perception that you cannot achieve error-free communication in a non-trivial way, that is, either without increasing signal power to infinity or reducing the data rate to 0 in the presence of noise. What he said, of course we'll have occasion to learn about his theory a little more in detail as we go along, but essentially the revolutionary thinking that he brought about was concerning the fact that in the presence of noise, the noise is not the ultimate limiting factor. The noise is the limiting factor, but it is not an ultimate limiting factor for reducing the data rate, or it is not a factor which requires you to put infinite power to get 0 error probability, right. What in fact he said was that if there is really a fundamental limit on the error on the data rate, suppose I denote the rate of transmission of data by f0. So his contention was that there is a fundamental limit on f sub 0, the data rate at which one can carry out transmission over a noisy channel, let's say a channel with a wide Gaussian noise. Fundamental limit in the sense that if you restrict your transmission of information at a rate less than a specific value which he called C, or which he called the channel capacity. So for a given channel he defined an attribute of that channel which he called the channel capacity, and the result that he propagated was that as long as you keep your rate of information transmission to be less than this number which he called the channel capacity, it is possible to achieve error-free communication. Of information, right. Now this was a very revolutionary result, and it sounded to be something against common sense, because from whatever we have developed so far, and the theories that I have told you are well understood theories, they are even modern theories, right, and there is nothing wrong with those theories that we have taught you so far, that their error probability becomes 0 only exponentially or asymptotically as signal to noise ratio is increased, and therefore signal power is increased or data rate is decreased. So on the one hand there is nothing wrong with those theories, on the other hand there is this result. There seems to be something wrong somewhere, right. There is actually nothing wrong, because the emphasis is on this word, transmission of information. Okay. What he said, and this is what is to be understood really, this result is not for transmission per se, error-free transmission per se, but error-free transmission of information in whatever you are transmitting. So the information content of a message can be made to reach the other side without any error, provided our information rate, mind you, this is also a limit on not the data rate, but the information rate is less than the so-called channel capacity, right. So basically every channel now has an additional attribute by which you can characterize it, that is the rate at which it can support transmission of information. So we have brought in an extra dimension here, and a dimension which we have not talked about so far. intuitively we all know that when we're talking about communication, basically we're talking about communication of information, and that aspect is what is really being emphasized here, that our interest is not in communication per se, but in communication of information.
That's not information rate.
That's right.
What do you mean exactly by information?
Data rate.
I'm coming to these discussions. Okay. So basically, to take up the kind of questions that some of you have immediately put forward as to what is the difference between information rate and data rate and things like that, before we can even take up the answers to these questions, even more important is to be able to define what we really mean by this so-called abstract notion of information, right? How can we make it more precise? So Shannon's contribution lay in giving a very precise mathematical formulation of information, and then based on that mathematical formalism coming up to a result of this kind. Right? This was his major contribution. Right? So let us try to understand what we really precisely mean by information, how we can define it or model it so that we can work with it in a more precise way. Right? And that's what information theory is all about, starting with a understanding of what is meant by information in a given message, how much information a message is conveying, and then working with this notion to derive the characterization of communication channels. Okay. So this is what we'll take up for discussion. So let's come to this question of how to define precisely what is meant by information. Now, there are two ways of looking at this question. One is what I call an intuitive way, and the other what we can call an engineering viewpoint. An intuitive viewpoint and an engineering viewpoint. Let's take the intuitive viewpoint first. As far as the intuitive viewpoint is concerned, the information content of a message can be linked to the element of surprise associated with a message, right? Element of new information that you are getting out of it, right? Basically, element of surprise. For example, let us say if you make statements of the following kind, that every day we have this class at 10 o'clock, or every whatever, Monday, Tuesday and Friday. You already know about it. There is nothing surprising about it. It doesn't convey you any new information except perhaps on the first day of the timetable when you didn't know when the classes will be. Or if I tell you that let's say Bangladesh has invaded India, let's say, right? Now that will be some element of surprise because you don't expect such an event. Or even for that matter, India has invaded Bangladesh or whatever, Pakistan or whatever. Although that is more surprising and therefore there is some information content in it, it's not as much as the other way around, right? So therefore, the intuitive viewpoint looks upon information as something connected with an element of surprise with a message, right? If there is a surprise value in the message, it conveys more information. If there is no surprise value in the message, it conveys less information, right? That's the intuitive way of looking at it. In other words, it's linked with the probability of occurrence of a message, right? Because something which is not surprising means it's highly probable and therefore conveys less information. On the other hand, something that has a very small probability of occurrence, if it occurs, when it occurs, it conveys a much larger amount of information. If somebody tells you that this is happening, then you feel that you are getting a lot more information than otherwise. Like for example, in stock exchanges, you can talk in the same way. A particular share is known to do well and it does well, no problem. But if on the other hand, certainly some unknown shares go up without the scam, then of course it's a different matter. And you could then take a clue that something is happening in the market which one should look into. Okay, so this is the thing here, linked with element of surprise. Now let's make it more precise. What we would like to see therefore is that if you want to develop a mathematical measure of information, call it I, it should be such that the information content is practically 0 if you're talking of an event which is associated with a large probability, right, as p goes to 1. Similarly, information content should become very large, let's say going up to infinity, as p goes to 0. So first we have appreciated that there is perhaps a link between information and probability of occurrence of a event, and the kind of relationship we are looking for is associated with these properties. So if you can think of a mapping from probability to information which has these properties, that would be a suitable candidate for a model for defining information, right? And one such model that emerges from these properties is that I is proportional to log of 1 by p, right? That is, as p tends to 1, this tends to 0. As p tends to 0, this also tends to infinity. Okay. Now this, then you can make it minus log of p, which is of course this, right? Think about it, why it should be minus and not plus. So this is from the intuitive point of view, if we proceed, this is what we get, this kind of relationship. If on the other hand we take the engineering viewpoint, an engineer's viewpoint, suppose you are an information engineer whose job was to help people pass messages containing information from one place to another. How would you like to look at information? You would probably link it up with how much time is required to convey a particular piece of information, so that if a guy takes too much time to convey his information, you could charge him more, and if somebody can do it quickly, you can charge him less. So somehow the engineering viewpoint could be based on the amount of time that it takes to convey a given amount of information, right? Make sense? Because then I can directly have, from an engineer's point of view, I have a way of calculating how much to charge him, right, for the services that I am providing him for letting him convey this information, right? If he uses a channel for more time, it must be that he is trying to convey more information. If he is using the channel for less time, it should imply that he is conveying less amount of information, right? So let's see if we base the thing on this. This is very satisfying from even some of the obvious examples that you might think of. For example, you are all familiar with Morse code, right? I'm sure some of you are probably radio amateurs, and even otherwise you are familiar with Morse code. What kind of code it is? It's full of dots and dashes, and if you look at the mapping from the English alphabet to this code, you will see some definite features in this mapping.
Greater the alphabet, the lesser.
That's right. Alphabets which are associated with let's say very large probability of occurrence, like E, so that means they are going to occur very frequently in a given text. So you don't want to spend too much time on conveying that, right? You will convey it with a smaller amount of coded message, so that it takes less amount of time. The overall text takes less amount of time to transmit. Similarly, a message which occurs rather infrequently, we don't mind if it is coded with a larger length of the code, right? Because it's going to happen so frequently that it is not going to affect your average message length very much, right? So in Morse code, more frequent alphabets associated with smaller code representations or smaller code lengths, and vice versa. Right? So this is intuitively appealing to an engineer because he wants to minimize the amount of time that he takes to convey a given amount of information, right? And he thinks that this is a good way of doing things. So somehow information is now linked with the time it takes to transmit a message. Now, to motivate the definition of information from this point of view, let's take a very simple example. Let's say we have to convey a binary message. Morse code is a much more complicated example. I'll take a very simple example where one is conveying what is called a binary message of the kind that we have been dealing with in digital communication, where in every let's say interval, some unit interval, you are conveying one of two possible messages, say M1 or M sub 2, and let us say they are both equally likely. They have each a probability of half of occurrence, right? Of course, in real life we could represent the message 1 with M sub 1 as 0 and M sub 2 as 1, right? That's the matter of representation. We can call them M1, M2 or 0 and 1. It doesn't really matter. Alright. So intuitively now you know how many symbols in 1 unit of time, whatever the unit of time I have selected, are required to transmit this information. 1 bit, because depending on what occurs, M1 or M2, I'll transmit this or that, but basically 1 bit of information or one, if a unit of information is bit in the usual sense, the amount of time required will be 1 unit time. In which will convey 1 bit of information, right? Suppose I now make this into a 4-level message, just for the sake of argument. Let's say now my messages are M sub 1, M sub 2, M sub 3, M sub 4, right? 4 valued message, that is in any in any unit of time, one of these 4 possible messages are to occur, right? So then what is the number of bits are required to represent it? 2 bits, right? So if the amount of time required to transmit 1 bit is fixed, then amount of time required to transmit information contained in this message will be twice as much, right? So if I say 2 bits, essentially I am also implying that 2 units of times are required. Of course, this is again based on the assumption that each of the 4 messages are equivalent, and so on. We can increase this argument so forth. But in any case, suppose I like to generalize this result to n messages, and let's say n is a power of 2 for simplicity, like we took 2, 4 and 8. What can we say about the amount of time that will be required? Log 2n bits, right? Log n to the base 2, or since it requires so many bits and time to transmit every bit is fixed, it requires so many units of time. So now we have seen what kind of relationship comes out, and what is the value of n in terms of, let's say, probability. If you take a take 4-level message, what is p in that case? Probability of occurrence of each message is 1 by 4 or 1 by n, right? In general it's 1 by n, so I can substitute n by 1 by p. So once again what I say is that the amount of time that will be needed will somehow depend on log 2 log of 1 by p to the base 2. Is it okay? So no matter what view you take, whether you take the intuitive viewpoint or the engineering viewpoint, you find that it seems a reasonable thing to associate a measure of information as some kind of a relation between this and the basic probability of occurrence of an event, and one could choose an arbitrary constant of proportionality here, and one usually chooses that to be unity and defines this as the information, and it's measured in terms of bits per message symbol or per event, right? That's the unit that you use based on this example that we just taken. For example, for a message which has 4 symbols associated with it, right, M1 to M4, occurrence of any one of these symbols conveys 2 bits of information, in the sense that it will require 2 units of time to transmit it, right? So that's a unit that we will associate with it, bits per message symbol. Sometimes it's briefly written as bits per symbol, right? Or sometimes even per symbol is omitted and we just write bits. But I think that per symbol is a very important thing which you should not forget. Even if you don't write it, it should be there in your mind, right? It's the amount of information as a result of occurrence of a specific event. That event is occurrence of a particular symbol from a dictionary of symbols. So is the motivation for this definition understood by everybody? Is there some question on which you like to discuss? Also, you could associate another interpretation with this, but I will come back to that in a minute. So I is equal to log 2 1 by p, and we could say that this you can also interpret as the minimum number of binary digits required to encode the message. This interpretation is based on the same example that we had just discussed. For a 2-message code, for a 2-message source, a source which emits one of 2 possible messages, how many bits are required, how many information bits are required to encode it? 1 bit. For a 4-message source, all messages equiparable, we require 2 bits. 8-message source, 3 bits, and so on. So in that sense, it seems to be also having this interpretation, minimum number of binary digits required to encode the message, right? To encode in the sense represented by several number of bits, appropriate number of bits. Now the next related concept is that of entropy. Not the entropy that you learned in your thermodynamics, but entropy as we define in information theory. Now this is an attribute of a source of information, right? It's an attribute of an information source. And precisely it is defined as the average information associated with any message from that source, average, on an average. So it's really speaking very briefly, average information emitted by the source per message, or per message symbol to be more precisely. I am deliberately taking our source here to be of the discrete kind, right? Because it it is very convenient to do the discussion for that situation. The source of information to be of a discrete kind, of the kind that we deal with in digital communication, right? But of course, a real source of information could also be a continuous valued source of information, like all of us are continuous valued sources of information, because our speech signal that we emit is really a continuous signal. One can also develop a corresponding theory for continuous time, and if we have time we will spend some time on that. But even working purely with discrete sources, one does not lose that much of generality, because we can always go from a continuous source to a corresponding discrete source representation through, let's say, analog to digital conversion or whatever, right? So at the moment our discussion will be with respect to discrete sources. So entropy is an attribute of an information source, and it's really defined as the average information per message symbol associated with that source. More precisely, let me make the notion very precise. Let me define, or let me consider what we call a memoryless source. A memoryless source is characterized by, first, a set of symbols, let's say n symbols, which I am designating by m sub 1, m sub 2, m sub n. So it's comprised of n symbols which it may emit in any given unit of time, and it's called memoryless provided that successive symbols that are emitted by it in successive units of time are statistically independent, right? They do not depend on what was emitted in the previous interval or will be emitted in the next interval, right? So memoryless implies statistical independence of, that is, they don't remember at all what was emitted before or what will be emitted later. Let us associate with each of these. I am going to generalize things a little bit now. So far our discussion is based on the fact that all of them are equiprobable message symbols. That is, the source can emit any of these messages or any of these symbols with the same probability. But now let me associate any arbitrary probability P1, P sub 2, P sub n with each of these symbols. So these are the symbols, these are the probabilities. Now what will be the information associated with emission of the message m sub 1? Log of 1 by P1. Similarly, information associated with the occurrence of M2 will be log of 1 by P2, and so on, right? So we can compute the information as each symbol is emitted. Now if I ask the question, what is the average amount of information associated with this source or which this source emits on an average, then obviously it will be the weighted sum of all these information values that we individually compute, and the weights will be nothing but the corresponding probabilities, right? So information content of m sub I, let's call this I sub I, and that's equal to log 1 by P sub I, and therefore average information per message symbol will be simply P sub I log of 1 by P sub I, or summed over I minus P sub I log 2 Pi. Okay, and the units will be bits, because are bits per symbol. Any questions? So the average information that is associated with the source again therefore depends on the probability distribution of the various messages in the symbol, and this is called the entropy of the source, right. This is precisely what you call the entropy of the source, or source entropy. So entropy is an attribute not of the communication channel but of the source of information. Remember that, right? It tells us how much information a source is emitting every time it emits a symbol, right? Basically that's what it tells us. Now suppose I ask a very simple question, since this entropy depends on the probability distribution of the various messages in this in the dictionary of the source, for what kind of message source, discrete message source of this kind, for what distribution will this entropy be maximum? Answer should be obvious, right? Entropy will be maximized if all the probabilities are equal, right? One can prove this formally. I think I'll leave that as an exercise for you to do yourself, alright? So the message, I'll just write down the result here. I'd like you to read the proof yourself or perhaps try to prove it yourself. Message probability distribution that yields largest or maximum entropy is the equiprobable distribution. That is P sub I, for all values of I should be equal to 1 by n, because the total number of symbols or messages in that source associated with that source is assumed to be n for all I. If I substitute that in the expression for entropy, incidentally entropy is usually denoted by this notation H, and sometimes you write an argument M saying that it is associated with a particular message source M, right? This just a notation. So this expression will then become minus 1 by n, right? I going from 1 to n. Since this is independent of I, this will become simply right n times this value, or simply log 2n, okay, which is interesting because we are familiar with this log 2n. In the context of equiprobable message source, we could interpret log 2n as the number of bits that will be required to encode that kind of source, right? Therefore, in general, entropy has earlier we discussed in terms of a single symbol. Now we are discussing in terms of a source on an average irrespective of its probability distribution. We could interpret entropy as some kind of a measure of minimum number of digits required to encode the messages or the symbols of the source.
So why minimum average number?
Minimum average number. Minimum average. Encode the source. But I'll return to that. That doesn't. This minimum aspect of this is something that I'm just telling you from an intuitive discussion here. There is a proper result in information theory which really emphasizes the minimum part of it. We'll talk about that later. Any questions so far? So what have we? Let's just stop for a minute and take stock of what we have discussed so far. We have discussed the following interpretations of information and entropy. We have looked at the engineering point of view of information, engineering definition of information, that is the information content of a message is the minimum number of digits required to encode the source, to encode the message, sorry, not the source. And HM is the minimum number of bits, average number of bits required to encode the source for each of its messages, right? And so when we looked at the engineering point of view, which is this, it's linked with the number of bits that are required to represent a message, right? Then the intuitive picture that we have seen is associated with a surprise element, right? In which case HM can be interpreted as the average amount of surprise or average amount of uncertainty associated with the messages per message of this source, right? Average uncertainty. So these are terms that you will come across when you are reading about these things. Average uncertainty associated with each message for a source.
So how do we get this? How do we say that this is average?
This is just a reinterpretation of our earlier discussion on measure of information, where we associated information content with element of surprise, element of uncertainty, right? The more uncertain an event, the more message it conveys, right? The more information it conveys, right? Sorry, say that again. What is it?
Correlating the definitions.
That's all. We had earlier associated information with uncertainty. Now we are just extending the definition to entropy. That was based on event based interpretation. Now with our single message based interpretation, now we are talking about an average over a source for every message that is associated with a source. So that's why it's average uncertainty per message for a source. And thirdly, we have a precise, we can view entropy just as a mathematical relationship between the probability distribution of the source and like this. So these are three different ways of looking at entropy. Here we look upon it as the minimum number of bits required, minimum number of binary digits required to encode messages of the source on an average. Here we regard it as average uncertainty associated with each message of the source. Here we just regard it as a pure mathematical relation, right? These are the three different ways of looking at it. Okay. Next thing we like to look at is the more precise relationship between what we call source coding and entropy. We have seen now that entropy is a very important attribute of a source, information source, right? And therefore that brings us to the subject of source encoding. So for information theories, therefore representation of a source is just about as important as finding a good means for communicating it over the channel, particularly with regard to the new result that we just discussed, which was given by Shannon. Because what Shannon said was, for it to be possible for us to convey information without errors, what is really important is we keep the information rate below some number for a given channel, right? So therefore it's now important to make sure that we don't use an information rate far in excess of what is permitted. It should be in fact less than that, and therefore it's very important that for any given information source that you might have, you represent the information coming out of that source efficiently. It has a particular amount of information coming in, but what an engineer has to do is find out what that amount of information is and to represent it and code it by binary digits by using an average number of binary digits no more than the average amount of information coming out of the source, right. If you don't do that, that means you might be doing a very inefficient job of information representation, right. Efficient information representation therefore is a very important concern of an information theorist, or in fact therefore a communication theorist, and that's precisely what we study under the title of source coding or source encoding. Okay, that is representing information coming out of a source with as few bits of encoding as possible. And we know what is the minimum number that is required. We have intuitively discussed a few times that somehow it is linked with the entropy of the source. Now we have shown that for equiprobable sources, we would like to discuss that for other sources, that entropy is the minimum number of bits required to encode a source. On the average. What I like to show is that if I take an arbitrary message source, let's say M1, M2 to M sub n, that is your M, message source M is a vector comprised of an arbitrary set of symbols with corresponding arbitrary probabilities associated with them. What I'd like to do is to show you that it's possible to encode such a message with a number of using binary digits such that the average number of binary digits required is HM. Is it obvious to you that it can be done? A scheme of some kind coming out in your mind immediately? Suppose I ask, because this is the interpretation we are giving to entropy, that is, it is the minimum number of bits required to encode the message on the average for various messages of the source. In other words, somehow implied by this is the fact that there is a practical procedure of mapping M1 to some encoded sequence of binary bits, M2 to a corresponding coded sequence and so on, such that the average length of that set of sequences associated with various messages is no more than HM, right. Does such a practical procedure occur to you? In fact, the first question that bothers us is, does such a representation exist at all? Because this is what is meant by efficient representation of information. Efficient representation means that if this is our feeling that no more than this number of bits are required on the average, then I must have at least one possible procedure by which I can carry out a mapping from this message symbols to binary digits such that the average length is no more than HM. For equiprobable sources it is very easy to do that, isn't it? No, the procedure, because I can associate, suppose I have a 4 symbol source, I have 4 messages, so I put any arbitrary set of 2 bits with any of these messages. So the coding procedure is very simple, but for an arbitrary source it is not obvious how we could do that, right. So first I would like to discuss that and then come to a very important result called the source coding theorem.
But haven't we assumed probability equal for all the symbols?
Yeah, we want to remove that assumption now. We want to be able to say that kind of result or give a procedure which is general enough for any probability distribution, for any kind of message source in which the probabilities may not be equal, right? We will take that up next time. Thank you.